So the session is being recorded. It will take us a little while to transcribe it because we have to put subtitles on. AI, machine learning can help a certain amount with that, but it does get very confused with some of the terminology and the names, so we have to vet it quite carefully. So yes, the session is being recorded. I'll email you afterwards with a link to that. But if you have any questions, please put them in the Q&A box at any point in the session, and we'll gather them up towards the end. Now, just as we're ready to get going, I've got two polls that I'd really like to share with you. First of all, is just to find out what level of study you're interested in. So if you could fill that in and let us know, we'd be very interested to know. So it's asking whether you're interested in studying a degree or an MSc or equivalent, or you're not actually here to inquire about study. So we'd be really interested to see your feedback on that. Very interesting. So at the moment, it looks like the majority of people are interested in studying a degree, and then a few more interested in doing an MSc or equivalent. We do an MRes in the department as well, and some who aren't here interested in study. So I'm going to finish that off. Thank you very much. And the next poll is really about whether you've got an offer already. We're just interested to know whether you are an offer holder, either with us or with somebody else, or you don't have an offer. So again, really interesting. Most people don't have an offer to study, so that's very interesting for us to know. And so about roughly split between people who have an offer to study here and elsewhere. Thank you very much. Really appreciate that. That helps us get an idea of the audiences that are joining us. So now that we've got the admin out of the way, and I've told you where all the fire exits are and all these things, I'm going to hand over to Dr. John Hales, who is going to give the presentation. If my screen goes blank at any point, I'm still around. I'll just be doing things in the background. Okay, over to you, John.
Hi, everyone. Thanks for joining us today. I'm just going to share my screen. Can everyone, is that good? Excellent. Perfect. Okay, so today we're going to be talking about virus lasers, which is the subject of my research program. So what is a virus laser? So virus lasers are a new class of a laser system in which the active component is composed of dye-labeled viruses. We're going to go into a lot more detail later on exactly what that means. But as an analytical technology, we're designing virus lasers for use as tools for making scientific measurements. Now, a big application in the future for virus lasers will be in helping to manufacture biopharmaceutical products, such as monoclonal antibodies, cell and gene therapies, and also vaccines. So as I'm sure you can imagine, this is a really hot area at the moment. And I think that virus lasers can play an important role because at the moment, manufacturers are really calling out for new analytical technologies. Now, based on the data that we've collected in the recent past, we think that virus lasers have a lot of advantages over the current analytical technologies available. For instance, we think they can be a lot more precise, sensitive, and can also operate in close to real time. So this is potentially high impact research, but like most research at the cutting edge, it's also high risk. It's also multidisciplinary in that it bridges laser physics and also molecular biology, and also our application spaces in other fields, so bioprocessing. That's one of the reasons why I'm especially happy about being based at the UCL Biochemical Engineering Department. So much of the research we do here is multidisciplinary, and it's also a great base to form collaborations, both with other researchers and also with industrial partners, including other companies who do manufacturing. That helps us keep the research really relevant. The department also has a very strong track record in commercializing its research so that the technologies that we develop get into the real world and have a real impact. So there's been at least a couple of successful spin-outs in the recent years from the department. And I recently founded Roxygen, which is a UCL spin-out. And what we're going to do is build a new platform for bioprocess analytics. And that will bring in the virus laser technology that we're talking about today. Then also another technology invented by myself and colleagues at UCL called decay-associated chromatography, but we're not going to be talking about that technology today. So to make all this happen, I'm currently funded by a UKRI Future Leaders Fellowship, and that's worth about £1.2 billion. Okay, so before I dive into the detail now, I've got another poll. So this will just help me gauge how to pitch it today. So if you don't mind, if you'd answer this poll question: how much do you know about laser physics? Are you an expert? Do you just have some knowledge or experience, or not much, nothing? There's no right answers to this question. I'm just curious to know. What the results, Kim? Oh, it's up.
So it just took a moment for it to get launched. The results coming through thick and fast. Okay, so with most people voted, the majority of people would say, well, 83% would say not much, not nothing, and 17% have some knowledge.
Okay, cool.
We don't have any experts in the audience, or people don't feel they're experts in the audience. They might be being shown.
Maybe soon, after this lecture.
Thank you.
Okay, right. Excellent. Okay, yes, that's the poll results. Fantastic. Okay, so I'll crack on then. So, okay, so before going into the more technical detail, I thought I'd give you an insight into my background, because I know a lot of you are interested in studying and maybe becoming researchers yourself. There is by no means there are people in the department have very diverse research backgrounds. This is just mine, and I'd probably say it's probably relatively unusual. So as an undergraduate, I studied physics at Oxford, and I found that as I progressed through my course and got closer to the cutting edge, I got more and more interested in the course. And by the end, I felt like my journey with science, if you like, hadn't quite reached a conclusion yet. I wanted to do more. In my final year, I did a major module on biological physics, and I felt like that was where the future was going to be. So that's what I wanted to get involved in. So I was lucky enough to get a place on a 4-year Wellcome-funded PhD program. And during my PhD at UCL, I invented the virus laser, which we're going to be talking about today. I subsequently joined the biochemical engineering department as a postdoc in Paul Dalby's group, who's also on the call. And it was during that time that we invented decay-associated chromatography. I subsequently had a Royal Society of Edinburgh Enterprise Fellowship, which helped me to consolidate the plans for the company Roxygen, and I'm currently a UKRI Future Leaders Fellow. Okay, so what came before the virus laser? So there's been a lot of excitement around nanotechnology. So a nanotechnology is a device or a material where at least one of the lengths, one of the functional lengths is less than about 100 nanometers. It's on that kind of length scale that quantum mechanical effects start affecting the properties of the material or the device. So if you're building a new material or technology, you have all of the classical physics up to a certain length scale. And then as you reduce those length scales into the nanometer region, you can start leveraging these quantum mechanical effects to make new and exotic types of technologies. So so people are interested in that, and then there came the observation that, of course, molecular biology is already at that length scale. So if you look at, say, a typical protein, a protein might have structural features on a sub-nanometer scale, which actually impact its function. So to illustrate that, on the left-hand side, you can see some electron microscopy images of some cadmium sulfide nanorods. And you can compare the morphology of that to tobacco mosaic virus, TMV, on the right. So you can see they both have a kind of similar shape, quite rigid. TMV really is that rigid. They haven't just kind of picked one that happened to be quite rigid. And in the bottom left, you can see almost kind of spaghetti of carbon nanotubes. And on the bottom right, you can see M13 phage, which is a type of virus. And you see how flexible that is as well. So then the question was, can you start using biological molecules to start building nanotechnologies? And the answer to that question was comprehensively answered as yes, you definitely can, by research through a number of groups. I think one of the groups that, whose work I certainly followed and was very interesting was Angela Belcher's group. And what they did is they took M13 bacteriophage, which is a type of virus that infects certain strains of E. coli bacteria, and they're able to use it and its structural properties to make different interesting materials, but where the kind of nanoscale aspect was relevant. So here on the right side, you can see a panel from one of their papers where they used M13 phage to make a lithium-ion battery. But as far as we know, no one else had the idea of actually trying to use this kind of stuff to make lasers. So that's what we're going to be talking about today. So this is a photograph of one of the early prototypes of the virus laser. Now, obviously, lasers themselves as a technology have been around a really, really long time. And I'll just go through some of the components that are true, have to be there in all lasers, what the key components are. So in this photo, you might not be able to see this particularly well on your screen, but on the left-hand side, you might be able to see a kind of very thin, slightly fuzzy blue line. And that's going from left to right. Can you see my mouse pointer at all or not? Okay, you can. Okay, so it starts about here and it comes into here. So that's the first thing that you need, and that's an energy in. So there's no free lunches. You need to have energy in to make these devices work. And in this case, that's coming from something like, well, a laser-like source. So that blue light enters what's called a cuvette, which is essentially a four-sided glass container. And you can see this liquid via these tubes kind of flowing in and out of that glass cuvette. So in this instance, this is fluorescein dye, which is being flowed through into the cuvette. Now the dye absorbs the blue light that's coming in from the left side, and then it emits green light in every direction. Some of that light is then trapped by what is called a resonant cavity. So that's the second key component you need in your laser system. So the resonant cavity is essentially two mirrors that are set in opposition to each other. So if you've ever been in a bathroom where you have two mirrors on opposite walls and you get that infinite reflection effect, that's essentially what the resonant cavity is doing. So some of the light that's emitted by the dyes will bounce against one of the mirrors, and then it will trace back along the same path and bounce to the other mirror, and it will be trapped between the two mirrors. Okay, so this is one of the interesting and maybe unexpected things that makes lasers possible. So when some of that green light passes back through the cuvette, it will actually trigger the emission of more green light in the same direction. Okay, so light will reflect off the mirror, come back towards the dye, and it will trigger more dyes to emit in the same direction and color. So you can imagine that this increase in light being emitted will then bounce across against the other mirror, bounce back towards the dyes, and then trigger even more emission of green light. And so you have an amplification in the light. You have almost like a runaway increase in the amount of green light being emitted. That light is then your laser light. So the third key component is that you need to have a cuvette with a material that will perform that amplification for you, and that's called the gain medium. Now, the final component of a useful laser system is that you need to have some way of extracting the energy or the light out of the laser system. Otherwise, it's not very useful. So in this early prototype, we actually used this contraption, which is a thin membrane, which was partially reflective. However, in subsequent prototypes, we actually removed this part and instead used the light that was transmitted through the back of the mirrors. So you can actually see that that's possible in this photo, because around the back of this mirror, you can see that some of the light's being transmitted. So that's a brief overview of how lasers work. What's unique about virus lasers? So a virus laser, in many ways, looks quite similar to what we saw before here in terms of the optical configuration, but the gain medium is composed of dye-labeled viruses. In the first manifestation, we used M13 bacteriophage. So that's the same M13 phage that was used to make that lithium-ion battery that I mentioned earlier. So the advantage in using a dye-labeled M13 phage as the gain medium, well, there's several advantages, but there's two main ones. The first main advantage is that you can chemically modify the coat proteins along the surface of the phage, so that you have dye molecules at specific positions, and you can decorate the surface of the phage so that there are dyes along the length of the virus. M13 is a long rod-like virus, which is about 1 micron long and about 6.5 nanometers long. But the dyes are only spaced apart by a few nanometers. So you can see that you can pack quite a lot of dyes onto one of these viruses. The second big advantage of using a dye-labeled M13 is that M13 can be programmed to bind, so to dock or to connect with other biomolecules. So a lot of measurements, a lot of the kinds of measurements that we try to make, we're trying to measure how much of something is present in a liquid solution. And a standard tactic for doing that is that you introduce something into the system which can generate a signal, but could also bind that target that you're interested in. Okay, and then that readout, that signal, will give you some indication of how much of that target is present. So M13 phage can be programmed to bind target biomolecules with a similar spec to the gold standard in this area. Okay, so you have your dye-labeled M13 and you have an optical configuration. You're now flowing through the dye-labeled virus through the optical configuration. How do you know that it's working? Is it just about a case of just generating a lot of really bright green light? Well, no, there's more tests that you have to do. There's actually several tests, but I'm going to focus on one of the more important ones. And that's that lasers, to be lasers, have to show threshold-like behavior. So this is illustrated in this graph, which I'll walk through now. So on the horizontal axis, this is the intensity of the incoming light. So this is the blue light that we were talking about earlier. Now notice on this axis, the ticks here are actually logarithmically spaced. What that means is that each major axis is actually 10 times larger than the previous one. So this is quite a large variation in the intensity of the incoming blue light. On the vertical axis here, this is the output from the laser system. So this is the green light that's coming out. Again, it's logarithmically spaced, and you can see that there's a very large range in the intensities of the output light. Now, so this orange curve here, this is a curve for when you introduce fluorescein dye into the optical configuration. We know in advance that fluorescein dye is capable of lasing. So this is kind of just a check that the system's working. So at very low input light intensities, you get almost no output from the laser system. Okay, at that point, you haven't put enough energy in to make it work. However, as you increase the energy, there comes a critical point, which is known as the threshold point, above which you have now put in enough energy to achieve lasing. And you see an extremely sharp increase in the output of the laser system. So a very small change in the input light results in a very large increase in the output light. And this is characteristic of lasers. So if you look at the other curves now, these are our dye-labeled M13 when that was flown through the optical configuration. And you can see a similar pattern. There's a sharp change in the output about the threshold point. Now, each of these curves actually represent a different concentration of the dye-labeled M13. And as it goes this way, the concentration decreases until you get to a point where you can see that the concentration isn't high enough for you to achieve lasing anymore. Okay, so how would you use that in the context of an analytical measurement? So this is something that we demonstrated in our research and was quite exciting. So quite often, what you're really interested in is whether the concentration is above or below a critical number. For instance, in the context of clinical diagnostics, there might be some biomarker, and if that biomarker is above a certain concentration, that might indicate disease. But then if it's below that that concentration, then there might not, everything might be good. Likewise, in a manufacturing context, there might be a level of a contaminant which is acceptable, but then above that point, then it ceases to be okay, and that might result in a failed batch. So what we've done here is that we've changed things up on the horizontal axis. So on the y-axis here, you've got the output of the laser system again, the green light's coming out. But on this horizontal axis now, instead of having a change in the input energy, the input light, we're changing the concentration of the dye-labeled M13, or as we sometimes call it, the virus lasing detection probes. Each of these curves then are at a fixed light intensity. So the amount of blue light coming in is equal for each of these different colored curves. So this is how it works. So let's say that you initially had a low concentration, say 100 picomole per mil of your dye-labeled M13. Then for this blue curve, which is a fixed energy input, you would have a very low output, a very low signal generated, demonstrated here on the cartoon on the left. However, if you were then to increase the intensity by just increase the concentration of the dye-labeled M13 by just 50%, then you would increase the signal up here, which is a very large intensity. So you can see that now a 50% increase has resulted in a large signal. In fact, a 50% change here from 100 picomole per mil to 150 picomole per mil results in an over 10,000-fold increase in the signal. Now, this is the largest responsivity ever observed in this kind of measure, in any kind of measurement system like this that we've ever, that certainly we're aware of. So if your critical concentration was, say, between 100 and 150 picomole per mil, as the concentration moved beyond that critical point, that would be readily obvious because of this very large change in the laser signal. This is a very unambiguous result. Okay, so to try and give you a little bit of a flavor of what research can be like sometimes, I wanted to kind of give you, tell you a little bit about what it took to invent virus lasers. So the photograph on the right here is a much later prototype of the virus lasers. You can just see by the density of the optics around the gain medium now that a lot more stuff has been added to try and refine its properties. So in developing a superior optical configuration, we introduced components to control the intensity of the incoming light and also the beam profile of that incoming light. In terms of the output from the virus laser, which now the light comes out of this mirror here through the back, it's transmitted through. We introduced optics to enable us to measure the light levels over a very large range. So we were able to measure a dynamic range of over 100 million fold. To put that into context, if you have a 30 centimeter ruler, the dynamic range, the difference between the largest and the smallest measurement that you can make is a factor of 300 millimeters to 1 millimeter. Here we were able to measure over 100 million. So aside from developing the optical configuration, there was also a lot of work involved in developing the dilabeled M13 phage themselves, in terms of the chemistry and also the growth and purification of the phage. And so even after doing all of the work to develop the biology, then also the optical configuration, at that point where we're starting to generate lots of data, actually it was so new that we didn't, the models to actually fit and interpret the data didn't really exist. So after doing all the work in the lab, there was then a substantial period of time where I developed, essentially crunched through all the algebra to develop new models to then fit that data to interpret it. Okay, so I touched on an important application for the virus laser being in manufacturing biopharmaceutical products. So I wanted to briefly give you a little bit of an insight into how biopharmaceutical products are manufactured, to put that into context. Now, I'm certainly not the number one expert on this in the department, but I'll do my best to give a very quick and maybe slightly crude explanation of how it works. So in terms of biopharmaceutical products, we're talking about monoclonal antibodies, cell and gene therapies, vaccines. In this example, I'm imagining your product is a monoclonal antibody, as illustrated here. So this is the actual medicine that you're going to inject into someone's arm, is hopefully going to treat them. So you start with a genetically engineered cell, which is capable of expressing this product. You then have to create an environment for those cells and supply them with the raw materials that they need in order for them to express that product. Now, having done that, you then have your product, but you also have the rest of the cell and all of the rest of the culture medium. So lots of different contaminants. Now, some of those are potentially harmful to humans. So then your next step is to try and remove all of the contaminants and leave your product. And it's in that phase, the downstream processing, that we think that the virus laser can have an impact. So why do we think that's the case? Well, currently the industry is calling out for new analytical technologies. Now, one of the reasons for that is partly because biopharmaceutical products are getting more and more complex over time. They're also getting more powerful and can treat many things that were maybe previously untreatable, but they are getting more complex, and maybe some of the old technology that we were using to make these measurements aren't really performing in the way we'd hope. Aside from that, there's also a question of trying to optimize the manufacturing process. So we think, our data suggests to us that virus lasers have a lot of advantages over the current state-of-the-art technologies. Give you, we've already spoken about how the responsivity of virus lasers, that's an ideal output if you want to integrate the output of these measurements into, say, a software control system for your manufacturing process. You're either lasing or you're not lasing. So that's a binary output, a 0 or 1, and that's exactly the language that the computer system might understand. Aside from that, though, you also need to make it very straightforward to make these measurements. And in this different set of experiments now, we showed how easy it is to make these measurements. So we demonstrated what we called a mix and measure measurement. So I'll talk through this graph now. So in this experiment, you start with your dye-labeled M13 phage, and we then at different time points, so on the horizontal axis, that's time, we added a antibody similar to the one in the drawing I showed previously. And then having added those antibodies and the dye-labeled M13 actually bound to each other. They form binding complexes. Now, the impact of that was to change the laser output. So that changed the laser signal. So if you look at the purple curve, you added the antibody, and then there's a very sharp decrease in the laser output. And that was indicative of the presence of the antibody. That then plateaus out, and then as you add more antibody to the system, you then see another drop in the output. Now, if you don't put enough energy in to achieve lasing, then you get what's shown in this green trend. So here, the output doesn't really change, even when you've added the antibody. And the time scale here for this change is about at the maximum rate at which this could possibly be observed. So this is as rapid as this kind of measurement could have been made. So how do we see virus lasers integrating into the manufacturing process? So we imagine that between the different unit operations of the downstream process, connecting a virus laser actually at line to the process itself, sampling from the process stream, and then mixing that with the dye-labeled M13. The resulting signal would then be indicative of the presence of the product or a contaminant, depending on what you're trying to measure. In this example, the virus laser might detect that the level of contaminant is too high, and then talks to a software system to then actually change something upstream to prevent the formation of that contaminant. To give you some context to how this sort of thing might work at the moment, we have industrial collaborators, and their experience is actually common across the industry. And so between each of the processing steps, they extract a sample, and they actually have to walk across the road to get to their quality control lab, where they do a whole suite of analytical tests, many of which take several hours. They can actually be 4 to 8 hours before the process can start again and proceed to the next stage. So this is obviously very inefficient, and the manufacturing process would be more productive if you could make these measurements in close to real time, which is what we're aiming to do with the virus laser. But it's not just about making things more efficient. We think that by making these measurements, we think that the virus laser will be able to make measurements that are actually more sensitive and more precise as well. So we think this will potentially make the process safer and more reliable, and potentially will also enable new modes of manufacturing. Typically, manufacturing happens in so-called batch mode, whereas we think that introducing these kinds of new analytical technologies will facilitate a move to continuous manufacturing. The key point there being that being able to continually make measurements very rapidly will enable new modes of manufacturing that are potentially more efficient and will reduce the cost of manufacturing. So what are the technical milestones for the project that I'm working on at the moment? So at the moment, one of the things we're trying to do is work out what the limit of sensitivity is for the virus laser. We're also very interested to find out how the structure of the lasing detection probes, the dye-labeled M13 in our example, impact the laser properties. So how does changing the number of dyes on the virus affect lasing? How does changing the chemistry on the coat proteins affect lasing? I think that's very interesting, and from a research perspective, but also from a practical perspective, because it might help us make more effective probes in the future. A very big goal for us as well is to actually demonstrate prototype systems in our application in a relevant context. It's okay being able to do things in my lab, but ultimately we want virus lasers to work in the labs of other researchers and also within industrial contexts. So to make that all happen, I was fortunate enough to be awarded a UKRI Future Leaders Fellowship. That's a fellowship that lasts 4 + 3 years, and the first 4 years are worth £1.2 million. So to give you an idea of what that pays for, so that will pay for my salary. It will also pay for the salary of another researcher to join the project. It also will pay for lots of new equipment in order to make these measurements, lab consumables, and also have a travel budget, but suffice to say that hasn't been going down very quickly. So I currently have a fairly sparse looking lab in the basement of the department on the UCL campus. currently buying lots of the kit and populating that lab. But I won't be based there for for especially long. The plan is for me to join the Manufacturing Futures Lab at UCL East. So if you haven't heard about this before, this is a very exciting development. So UCL is building a new campus on the former Olympic site near Stratford, or in Stratford. And on level 7, there will be the Manufacturing Futures Lab. The aim is to become a global leader in manufacturing research. This is highly multidisciplinary. The biochemical engineering department is one of the departments involved, but there's several others. So that's going to be very, very exciting. So watch this space on that. The last thing I wanted to do is to acknowledge the generosity of all of the funders that I've had over the years. And last of all, well, I'd also like to thank you all for joining us today. And lastly, before we open up to your questions, we have one more question from us. And that is, did you learn enough today to explain virus lasers to a friend?
Well, thank you very much, John. That was great. I'd also like to say, just a shameless plug, there's a slide in the background of the Here East image that John showed. That slide is great fun, and you'll scream a lot going down it. Thank you. So the answers are coming from that. John, I'm going to end the poll and publish that for you. Great. Thank you very much for your responses there. We've got quite a few questions come in. There's some really good questions come in. What I'm going to do is I'm going to leave John and Paul, if you're available. Paul, if you could have a look through those questions, and between you, think who's going to answer them, whether you want to group them up into sections. John, you may have actually addressed some of them in the presentation because the questions were coming throughout. But just before we get, just whilst Paul and John are looking through those, I just want to say that we've got a biochemical engineering MSc Q&A session on Friday. Professor Dan Bracewell is going to be available to answer any questions you've got about studying an MSc with us at biochemical engineering. I also want to let you know that UCL has moved its deadline to the 31st of May for all its postgraduate talk programs. So if you are interested, because we've been especially popular this year, many people have wanted to study a postgraduate degree. UCL has brought its deadline forward. So you're more than welcome to join myself and Dan Bracewell on Friday. I'll put a link in the chat so you can sign up to that. But do bear in mind that the deadline is fast approaching for that. If you're interested in studying a degree or just want to know some more about studying a degree at UCL, UCL's undergraduate open day is in June. Myself, Dr. Brenda Parker, Dr. Chika Nweke, we'll be around in 2 sessions, one at 12 o'clock and one at 5 o'clock. So come along and talk to us. You can talk to Brenda about any of the degrees we do, any questions you've got about studying, about the department. We'd love to talk to you about that. We can go into much more detail, obviously, than we can here. I'll put a link to that as well. And the final thing that I'll put a link to is a survey to ask how you thought we did. We do really appreciate your feedback. So what I'm going to do now is I'm going to hand over to, first of all, Paul. Paul, if you'd like to introduce yourself, and then between you and John, if you could answer the questions, that'd be great.
Sure, very quickly. So I'm Professor Paul Dalby in the Department of Biochemical Engineering. I'm also, as you can see in that side logo in the back, one of the directors of the Future Targeted Healthcare Manufacturing Hub, which is a industry-sponsored and partly and also UKRI sponsored initiative to look at manufacturing and formulation of therapeutic proteins. Okay, so I guess, John, do you want to pick off some of the questions in the Q&A first?
Yeah, I had a quick look through. So there's no upvoting system here, is there? It's just, so I'll just go from top to bottom then. There's quite a few, so I won't be able to dwell too long on each question. So apologies if you think my answer's a bit brief, but you can always contact me and we can talk about it more as well. Okay, so the first question is, could you give some information on the risks you face in your research and how you mitigate, manage, or avoid these? Okay, so the main risk is the laser light itself. So we introduce various safety mechanisms to prevent the laser light getting into the user's eyes, or indeed anyone else who happens to be in the lab. The main safety things we do are we have a special lock on the door, so that only people, so if someone comes in without typing in a code, maybe they're not aware that the laser's there, then it will stop the laser from working. We also have lots of metal shielding to prevent stray light getting into people's eyes. We wear safety goggles and so on. In terms of the biological risk, we don't use dangerous biological materials here. So the virus is a bacteriophage that only in fact infects certain strains of E. coli that we have in the lab. So they don't pose any risk to people. Okay, so next question. Are virus lasers able to replace other methods that require the binding of a biomolecule to a ligand? If yes, how much more effective is the method? Okay, so good question. And we see virus lasers as a platform that will directly compete against the most common methods for these kind of ligand assays. For instance, ELISA. The big advantage being potentially the sensitivity, the precision, and the rapidity with which the measurements can be made. And also being able to get very unambiguous answers. I think anyone who's done ELISA before knows that getting an unambiguous answer is usually a bit of a challenge. Can you give an example of the analysis that you want to carry out with the virus lasers? You explain varying the concentration of those control the light intensity. How does that help in the analysis? Okay, right. So typically in these kinds of assays, let's say you have a target biomolecule. So this is maybe a very general, simple assay that might be commonly used in labs. So you have something that generates a signal, your detection probe that binds the target. You then have some way of isolating that complex, maybe on a surface or through some methods of purification, and then you're able to then read off that signal, and then the intensity of that signal is going to be proportional to the amount of the target that was present. Well, if I can, I might even let me.
I just want to quickly, just whilst you're doing that, just want to say, Paul's actually answered one of the questions in text. I'm just going to read this out because if anybody's watching this recording of this, they won't see the text. But somebody asked, can virus lasers be used to deliver therapeutics inside living systems? And Paul said viruses are fairly stable, such as against degradation by heat, etc. I'll try and publish these things in a blog, but what we'll try and do is we'll try and answer these verbally, because otherwise people watching won't have seen Paul's great answer there. So just to let you know, thanks.
So just quickly finishing off that answer. So one of the big advantages of lasing is that you can, so you remember that graph I showed with the threshold points. So instead of measuring the output of the light intensity, which is what you'd have to do during a fluorescence measurement, you can actually measure the position of the threshold point. This actually blends into this next question as well, which is what arguments would you give for using this system as opposed to classic fluorescent labeling? Okay, so instead of measuring the output intensity as your signal, you can instead measure the position of that threshold point. Okay, and then in this graph here shows, I hope you can all see, shows that the position of that threshold point can be related to the concentration of the detection probe. And that's significant because typically in, say, fluorescent labeling, the signal is very weak. Okay, so you need really sensitive optics in order to make that measurement. It's quite hard to make those measurements very accurately and precisely. Here, though, you're essentially measuring the intensity of the incoming light. because that's what determines the threshold point, right? So because the threshold point is either blindingly bright or not there, okay, you can then vary the input light to see at what point that happens, and you can measure that point very precisely. So you can measure the threshold point extremely precisely and then infer the concentration from that. I hope that makes sense. So that's a slightly different paradigm for making these kinds of measurements, a little bit more technical. There's a big advantage of using laser systems instead of using fluorescence systems. So there are lots more arguments for why you would use lasing instead of fluorescence. It depends. Obviously, it depends on the context. If you're doing some kind of microscopy, you might use fluorescent labeling. Okay, so if I stop sharing now.
Yeah, I'm sorry, Paul. Can I just ask a quick question? I mean, when John joined the department, he was also working with the London Centre for Nanotechnology. What is the context of John's work in relation to biochemical engineering at UCL? I think it's quite interesting to know how it fits in with, because you're also the director of research in the department. So could you give some context?
Yeah, so I was also collaborating with somebody at the London Centre for Nanotechnology, and it was kind of all happening kind of in parallel. We were doing another project with them. And so I was kind of aware of what John was doing at that time. And then as it moves forward, usually you're looking for sort of the next thing to do, the next grant to write, etc., the next part of evolution of the project. And so at that point, it kind of came together. We were evolving our projects, and we brought John in on that project. But of course, what he's already doing was this phage lasing work as well. So, we kind of allowed that to continue because it obviously had its own part to play. And I think, from what I'm aware, it was already connected into the department or into bioprocessing, and the likes of John Ward were kind of involved and had already plugged it in. So it was just kind of a continual evolution of that, really. We wanted to support it as much as we could.
So I'll move on to the next question. So are virus lasers faster than other methods used to determine quantity of a biomolecule by biotransformation? And the answer is yes. So the mix and measure assay that I showed, that happens as quick, the response to that happens as quickly as the binding between the probe and the target. You can't get faster than that. That's the speed limit, if you like. And if you could do that at line, which was, we're very determined to be able to do, it's our big research focus, then that would be a lot faster than the current techniques, which require walking across the road to make those tests. Would the output continue to decrease once more antibodies are added to the solution? Yes, it would do. And it would continue to do that until there comes a point where where there's no more, you can't put enough energy into the system anymore to observe lasing. In the industry, have you got an estimate as to how much benefit we could get compared to the cost of the virus laser? So you've got to factor in the cost of the analytical testing currently, which is extremely large. And you've got to factor in the loss of process intensification because you're pausing the process to make some of these tests. You're imagining being able to go from one unit operation to the next without pausing because you're confident enough that the virus laser is detecting all of the relevant contaminants at that stage and the concentration of the product if that's desired as well. So that so I guess if you're a contract manufacturing organization, you are just getting through more processes per year than you would have been doing otherwise. If you're interested in moving to continuous manufacturing, which I know a lot of companies are very interested in doing, but feel like maybe the technology isn't quite there, especially on the analytics. This is the kind of innovation that we're hoping will be able to make that possible. At the moment, if you're measuring continuously, you need to have your analytical team running 24/7, constantly making measurements, whereas this is the kind of thing you plug in and you're getting that data continuously.
I'd just add to that, there's lots of different ways you can measure benefit in terms of money in industry. So one example of that is, they say if you haven't got your product on the market, it's costing you $1 million a day, right? Because there are other competitors getting things on the market and you lose patent lifetime, and that's how much. So if you can get even a day earlier to market, you've just made £1 million. So, or $1 million rather. So that's one way, and the other way is cost of goods. If you can bring down cost of goods on manufacturing by even 1%, that's a significant amount of money. So I think the value you can bring is very quickly gained.
How does it work in terms of scalability of the design? I mean, is it something which, what's the cost of actually making the kit, and is it possible to look at making it more compact, and how does that work?
Yeah, I mean, that's a big focus of our research is we're building prototype instruments that will be have a compact enough footprint and a robust enough profile that you could integrate it into a manufacturing context. You don't want a very delicate liquid handling robot in that kind of context. So yeah, that's something that we're working with. One of the things I'm funded to work on. What exactly is lasing? Lasing is, I don't know if it's an acronym or an initialism anymore. You get picked up on that, but laser stands for light amplification by the stimulated emission of radiation. When you have light that's being amplified by that stimulated emission process that I discussed, remember where you had the green light passing back through the cuvette and then triggering more emission in the same direction, the same color. A device that's using that mechanism to generate a often intense single color beam of light, then that is laser, and that is the lasing mechanism. Please explain the interaction between the contaminant from the reactors and the virus. Sorry, please. Okay, the interaction between the contaminant from the reactors and the virus in the virus laser. So this is something that's common to a lot of how these sorts of measurement systems work. So it's a non-covalent, so it's not a chemical bond that's being formed between the two things. They kind of essentially, the surface of the probe, the proteins on the surface of the probe are essentially sticky for that target molecule, but they're not for the other molecules that are present in the system. It's a non-covalent interaction between the two particles. It's something we could talk a lot about. I don't think we've got time for, unfortunately, sorry. Are there other bacteriophages that could be programmed to bind to target molecules? Yes, absolutely. That is definitely possible. You explain the use of antigen to bind with M13 virus, which then changes light intensity. What is the objective of the measurement? Let's say that you had so in fact, in that experiment, we added liquid solution to the dye labeled M13, and there was no antibody present, and then there was no change in the laser output. But then you add in a sample that did have the antibody, and then you can see that sharp change in the laser output. And therefore, that change in the laser output means that you just added a sample that had the antibody present, which is the information you wanted to know. What was the greatest challenge so far during the research and prototype manufacturing process? Greatest challenge. Many things, some of them scientific, some of them not. I would say that some of the biggest challenges were actually around the modeling of the data, because it's such new stuff. We really had to get into the theory, really understand it in depth to really make sure that we understood it, which we did. But I think when you start with a blank slate, like a blank optical table, and start building the instrument, that's an exciting time, but that's also extremely challenging as well. Would a virus laser based assay need a wash step as in ELISA? No, not in every type of assay format. So you can use the virus laser in different ways. You could use it in a similar way to ELISA potentially, but you don't have to. And we have demonstrated an assay where you didn't need any wash steps to get a clear answer. Are there other virus laser research going on in other universities or other countries? How are they different from UCL research? There are other research groups studying other biological lasers, but as far as we're aware, there isn't any active research programs into virus lasers at other universities. It was invented at UCL, so I guess we've got a little bit of a lead. But there are other biological laser groups who do some great stuff as well. Their systems tend to be quite different to the virus laser system though. How many years would it take to commercialize the virus laser for industry application? How big is the potential market size? So we're looking, I guess it depends on what stage, but we're looking at a kind of 3 to 4 year timescale before we would have systems which could potentially be integrated into manufacturing processes. And how big is the potential market size? It's very large. You got to remember that a couple of years ago, the biopharmaceutical market was worth about $250 billion. About a third of that money is spent on manufacturing, and a large chunk of that is spent on analytics.
So I'm afraid I'm going to jump in here because we're coming quite close. In fact, we're just about to finish off, but we've got time for 2 more questions. But just before we do that, I just want to say I'm going to put a link to, I'll just put a link to a survey. If you could open that and then finish it and let us know afterwards how you found this session, that'd be great. But we're coming up to the end, so I'm going to ask John to look at the questions that we have and choose the 2 that he thinks he's got time to answer between him and Paul, and then we'll wind it up.
I think we've only got 2 more questions left.
Oh, fantastic! Perfect.
So why green light for the virus laser? Fluorescein dye was an attractive option because it could be excited with blue light. Shorter wavelengths are harder to generate than blue light, so hence fluorescein, and fluorescein emits in the green. In the antibody example, am I right to say they will only work for antibody of M13 virus used in the laser? If you want to test the presence of another type of antibody, then you need to use different viruses in the laser, right? Yeah, if you want to bind a different target, then you'd need to program the virus to bind that different target. It will specifically bind a specific target.
Great, thank you. We got through all of them. That's fantastic. I think that's it's a great achievement. Thank you. But thank you very much, John. We've had some very kind words in the chat box, which you may not have seen, but thank you, John. Thank you, Paul. And a huge thank you to everyone who posted these questions. They've been really interesting. Somebody did actually say, are you going to be doing any more presentations for prospective PhD students? And we try to get a balance in the taster lectures. So we cover things like vaccines and cell and gene therapy, which are core parts of the talk programs. We've also got this, and we've got one coming with Emily Costas and Gary Lai, which is going to be on bioprocessing of seaweed. So there are elements of research we do. We're also trying to cover parts of the talk programs as well. So have a look through the program. Next year, we'll see what other research which other researchers are happy to present in the same way as John has. It was very, very kind of him to take time out to do this. But just thank you very much. I hope you have a great afternoon, and I hope you enjoy the rest of the sessions. And for those of you who go on offer, we really look forward to welcoming you at UCL and seeing you in person in the future. So have a great afternoon and goodbye.
Thanks, everyone.
Thanks. Bye-bye.